discussing one more problem in material balance with chemical reaction. Let us read the problem carefully. SO2 reacts with pure oxygen to form SO3. The reaction is oxidation of SO2 to form SO3. If the reaction is carried out with twice as much oxygen necessary for complete combustion. See, certain words we need to underline. Complete combustion. So the conversion is what? Complete conversion. And oxygen is taken twice as much required for that, theoretically required. And to form reaction is carried out with pure oxygen, but under low temperature and pressure. The reaction goes only to 60% conversion. Actual conversion is 60%, but oxygen supplied is calculated on the assumption of how much is required for complete combustion, twice of that, like that. So calculate the average molecular weight of the product mixture. Here the question is what? Average molecular weight. The formula of if we okay, first shall we start the block diagram. Okay, so here this is the reaction. SO2 reacts with pure oxygen. SO2 plus half O2 gives SO3. This is the reaction. Okay, this is the reaction. Now the reaction is conversion is 60% conversion. Conversion is 60% conversion. So water entering this process, one is SO2, the actual reactant, and it is reacted with pure oxygen, not air. This is the for last class problems, air was supplied. Here pure oxygen was supplied, so only oxygen, no nitrogen. So this problem will be little simple compared to the last class problem. No nitrogen here, only oxygen, because it is given that it is pure oxygen. And if the reaction is carried out, this sentence is to calculate oxygen amount that is supplied. Now, what are the products that are formed? First, the actual product, first list out what are all the components that are forming. So the actual product SO3 will form, and oxygen is supplied in excess. So that excess oxygen will be leaving. Excess oxygen will be leaving, and there won't no nitrogen here. And then conversion is only 60% conversion. Therefore, the remaining 40% unconverted SO2 will be there. Okay. So the actual SO3 that is formed, and whatever the excess oxygen that is there, and unreacted SO2. Only three components are there. Now the question is calculate the average molecular weight of the product mixture. Average, first we shall plan out how to work out the problem. Average molecular weight of product mixture is how much? That means this is the product mixture. Okay, this is the product mixture. What is the average molecular weight? How to calculate the average molecular weight of this product mixture? Okay, the formula is sigma is equal to sigma MIIChE, where I equal to 1 to m. First we are planning out the solution. So, okay, so sigma MIIChE, that is the average molecular weight, where m is what? Molecular weight of component I, and YI is what? Mole fraction of component I. Okay, mole fraction of component I. That means we know the mole fraction of component I. We know the molecular weight of component I. Mole fraction we need to find out. I equal to 1 to n means how many components are there here? 3 components are there. That means m of SO3 into y of SO3 plus m of oxygen into y of oxygen plus m of SO2 into y of SO2. This is the average molecular weight of product mixer. This is our plan to solve this problem. Okay, average molecular weight. You know the molecular weights, you know. Okay, then we need to calculate what? Mole fractions of this. And in last class also we have calculated mole percent, we calculated now. So same way we need to calculate by writing material balance for each component, calculate how many moles of each component are leaving. Okay, then don't put 100, you will get a mole fraction. Then you substitute, you will get the average molecular weight. Okay, so now we shall start with some basis here. First the reaction, again if you write the reaction here, SO2 plus half O2 gives SO3. This is the reaction. Okay, equation 1. This is equation 1. Okay, now what is your basis here? Basis is, let us take the according to stoichiometry only. So 1 gram mole, shall we take 1 gram mole here? No units are mentioned. You can take either kilomole or gram mole. So 1 gram mole of SO2 fed. This is our basis. So SO2 charged is equal to 1 gram mole. Okay. Then SO2 balance you can write, isn't it? So SO2 balance is what? SO2 balance is what? SO2 charged or fed equal to SO2 reacted plus SO2 leaving. I told you in last class, you can also calculate in another way. Here 60% converted, so the remaining 40% is SO2 leaving. That is more simple calculation. So SO2 reacted how much? SO2 reacted is how much? 4 mole. 1 mole we have charged, but conversion is only 60%. So 0.6, that is 0.6 gram moles. That is SO2 reacted. So SO2 leaving is equal to SO2 leaving, this one, SO2 charged minus SO2 reacted. Charged is 1 gram mole, reacted is 0.6, that is 0.4 gram moles. Okay, this is SO2 balance. So put a tick here, SO2 calculation is completed. Or another calculation, 60% is converted, the remaining 40% is leaving. Okay, next. SO2 is over. Then oxygen. Oxygen balance we write. Here, oxygen balance is what? Oxygen supplied is equal to oxygen used up plus oxygen leaving. This is oxygen balance. We need to calculate oxygen leaving. Okay, this is how much. So we need to calculate first oxygen supplied and oxygen used up. So oxygen supplied. For this, what is given in the problem? We need to read out carefully. Oxygen is supplied twice the amount. Twice the amount. This is very important point. Twice the amount that is required. That is required for complete combustion. Okay, for complete combustion of SO2. This is given. This is very important point. Okay, oxygen supplied is equal to twice the amount that is required for complete combustion. Here 1 mole we have taken as the basis. So for complete combustion, actually complete combustion is not taking place. That is a different thing. But calculation of oxygen supplied should be based on what is given. Okay, this is a different calculation. So complete combustion means our basis is 1 mole of SO2. Okay, 1 mole of SO2. For complete combustion of 1 mole of SO2, how much oxygen is required? So how oxygen required for theoretically required, you can say oxygen theoretically required for complete combustion of SO2. How much? Half mole, that is 0.5 gram mole. Okay, that is 0.5 gram mole. Next, therefore oxygen supplied is how much now? Oxygen supplied is twice the amount, that is 0.5 into 2, that is 1 gram mole. Twice. Okay, so like that we calculate. Last class also I explained you oxygen supplied calculation you need to do carefully depending on the information given. For some over 20% excess over theoretically required, like that it will be given. Here twice as much required if oxidation is complete. So that is 1 gram mole. Okay, so now oxygen supplied we got. So oxygen used up. Oxygen used up how much now? Oxygen theoretically required into fractional conversion. Fractional conversion. So theoretically required how much? 0.5 according to stoichiometry. Theoretically required means fractional conversion is 60%. That is 0.6. Therefore, this is 0.3 gram moles. Okay. Oxygen theoretically required is 0.3 gram moles. Therefore, oxygen leaving is equal to oxygen supplied minus oxygen used up or consumed, anything used up. So oxygen supplied is 1 minus 0.3, that is 0.7 gram moles. Okay, this is oxygen leaving. So oxygen leaving we got SO2 over, then SO3. Then SO3 leaving is equal to how much SO3 has to be found? 1 mole is to be found. But what is the conversion? 60%, that is 0.6, that is 0.6 gram moles. Okay, according to stoichiometry, according to our basis, when 1 mole of SO2 is reacting, 1 mole of SO3 need to be formed. But conversion is only 60%, so 1 into 0.6 gram moles of SO3 will be formed. Okay, so now we calculated the number of moles of each component. Now we shall list out the moles of each component. So gases leaving. How much? SO3, 0.6 gram moles. Then oxygen Oxygen how much? 0.7 gram moles. Then SO2 0.5 gram moles. You will get total gram moles. Total moles leaving. Total moles leaving. Okay. So total moles leaving is how much? Total moles leaving is 1.7. 1.7. Okay. So now we need to calculate mole fraction of gases leaving. Mole fraction of SO3 leaving. SO3 leaving. This is represented by Y. Y is the mole fraction of SO3 leaving. Mole fraction of SO3 leaving. That is 0.6 by 1.7. Okay. Then mole fraction of oxygen leaving. This is given by Y oxygen. That is 0.7 by 1.7. And mole fraction of SO2 leaving. Y SO2. This is 0.4 by 1.7. So mole fractions you need to find out. SO2 is 0.235. 0.235 and SO2 is no, this is 0.235 and SO3 is 0.352 and oxygen is mole fraction of oxygen is 0.41. Okay, thus we calculated moles by total moles. Mole fraction Y equal to moles by total moles. This is mole fraction. Okay, thus we got. Then molecular weights. Molecular weight of SO3, that is MSO3, is how much? Molecular weight of SO2, MSO2, and molecular weight of oxygen, M oxygen. This is 32. 32 plus 32, that is 64, and 64 plus another 16, 71 plus 7, 80. Okay. Therefore, average molecular weight. Therefore, average molecular weight of product mixer is equal to MSO3 YSO3 plus M oxygen Y oxygen plus MSO2 Y SO2. So MSO3 is 80 into YSO3. YSO3 is 0.352 plus M oxygen is 32 into Y oxygen is 0.41 plus MSO2 is 64 into YSO2 is 0.235. Okay, so this you will get 56.32. Okay, this is the answer. So in this problem we calculated average molecular weight. In previous problem composition, there it was stopped with composition, percentages into 100 we did. Here little more, that is average molecular weight we calculated. Thank you.